Okay, welcome back to our discussion on transportation problems. In this video, we will carry out the stepping stone method for our first example. However, you must see the video first on closed polygonal paths and improvement indices in order to understand this video. Okay, what is the stepping stone method? The stepping stone method is a way of checking whether our allocation of supplies is optimal or not. By optimal, we mean that it gives the minimum transportation cost. Basically, the stepping stone method tells us whether we can still lower the transportation cost or not. As mentioned in the previous video, the stepping stone method requires the notion of closed polygonal paths and the improvement indices. If the improvement index is positive or zero, this means that moving supplies according to that polygonal path will give us an equal or higher transportation cost. Whereas if the improvement index is negative, this means that the transportation cost can still be lowered by moving supplies according to the direction of the closed polygonal path. So what this means is if all the improvement indices are positive or zero, this means that the transportation cost cannot be lowered anymore. But if an improvement index is negative, this means that it is still possible to lower the transportation cost. So now let's carry out the stepping stone method for our first example. From our first example, we have this transportation model, and after doing the northwest corner rule, we have the transportation cost amounting to $7,300. Now let's check if we can still lower that $7,300. So notice that here the unused cells are West Town A and East Town C. So let's compute the improvement index of West Town A. So we have this closed polygonal path, and then computing the improvement index, we have 6 minus 10 plus 6 minus 8, and this gives us negative 6. So we got an improvement index that is negative. So what this means is moving supplies in this direction will give us a lower transportation cost. So in other words, the $7,300 transportation cost can still be lowered because we have an improvement index that is negative. Now let's try to compute the improvement index of East Town C. So computing the improvement index of East Town C, we have this closed polygonal path. So to compute, we have 7 minus 9 plus 8 minus 6, and that is equal to 0. So because the improvement index is 0, this means that moving supplies in this direction makes no change in the transportation cost. So let's summarize our improvement indices. So we have negative 6 and 0. Now, in order to give us the best possible improvement of our transportation cost, we have to take the most negative improvement index. The reason for this is because the most negative improvement index will give us a substantially higher deduction of the transportation cost. Now, so we will pick this improvement index because it is the most negative. And take note that this improvement index was computed using this closed polygonal path. Now notice that in the computation of the improvement indices, the negative signs are 10 and 8. So these two negative signs correspond to the cells East Town A and West Town B. So let's put these numbers 250 and 300 inside the oval. Now what this oval means is we will move objects from these cells. Now the question is, how many boxes of chocolates should we move in order to get the most deduction in our transportation cost? So to answer that question, okay, between these two numbers, these numbers corresponds to the negative signs in our improvement in the computation of our improvement indices. So what we will do with these numbers inside the oval is we will take the smaller of the two values. So between 250 and 300, the smaller of the two values is 250. So what we will do is we will move 250 from this cell to this cell, and we will move 250 from this cell to this cell. In other words, we will subtract 250 from each number inside the oval, and we will add 250 to cells in the polygonal path that are outside the oval. So we have this animation. So subtract 250 here, subtract 250 here, add 250 here, and then add 250 here. Now when you do that, you will get an updated transportation model like this. Now because we updated our transportation model, we have to compute the transportation cost. So now the transportation cost is 350 times 6 plus 250 times 6 plus 50 times 8 plus 200 times 9. So that gives $5,800, which is significantly much lower than the previous transportation cost of $7,300. Now, we have improved our transportation cost using the stepping stone method. Now, the question is, can we still lower this $5,800? So to check, we have to do another round of the stepping stone method. So to check if optimality is achieved, we compute the improvement indices again of the unused cells. So now this is our improved transportation model with a transportation cost of $5,800. The unused cells are East Factory Town A and East Factory Town C. So let's compute the improvement indices of these cells. So we have this closed polygonal path and this closed polygonal path. Computing the improvement indices, we see that there is no more negative improvement index. Now, what does it mean if there is no more negative improvement index? Since there is no negative improvement index, this means that optimal transportation cost is already achieved, which means that it is no longer possible to lower the transportation cost. And hence, the transportation cost, $5,800, is already the minimum transportation cost. So we have a minimum transportation cost of $5,800, and this one is achieved by allocating our supplies in this way. So this ends the discussion on example 1. For our next example, please go to the next video.